I'm Ye Haoyun from Group 5, and today I will introduce our project, Neural Care AI, a research project that applies a machine learning framework for early dementia diagnosis. This is our outline. Let me first discuss our research motivation. According to the World Health Organization, over 55 million people globally are affected by dementia, with 10 million new cases annually. More importantly, current diagnosis cases and method often face delays which not only limits timely treatment possibility, but also increase the burden on healthcare systems. This urgent need drives us to develop better early diagnosis tools. During our research, we identified three main challenges. First, the complexity of multi-dimensional data integrations. Second, the data imbalance problem, which directly affect model accuracy and reliability. And third, scalability issues, as we needed to ensure the model can operate efficiently in different healthcare environments. Specific, specifically, current diagnostic method mainly rely on clinical evaluation, neuroimaging, and biomarker analysis. These methods are not only resource intensive, but also require significant time in investment from professional experts. Meanwhile, the increasing number of dementia patients puts enormous pressure on the healthcare system, slowing down the diagnostic process. And there are also data and scalability issues. Therefore, our project aims to develop a machine learning diagnosis pipeline, hoping to address data imbalance through data augmentation techniques, improve model interpretability through feature selection, and optimize ROC AUC performance to exceed 70%. This is related works. And regarding related work, we have found application of machine learning in early Alzheimer's diagnosis. Existing research faced two main challenges. First, early diagnostic accuracy, where traditionally diagnostic methods often lack accuracy in early disease stage and face difficulties in integrating multi-dimensional medical data. Another significant challenge is model selection and evaluation, as different machine learning models show varying performance across scenarios and lack a unified evaluation framework. Current research primarily employs three methods supporting vector machine, random forest, and the XGBoost. This method use cross-validation to ensure reliability and small technology to address data imbalance. However, these studies have limitations. First, they only tested three basic models and lack model ensemble strategies. Finally, they lack automated model selection mechanism. Therefore, we can consider more diverse models and ensemble methods, as well as introduce tools like Optuna for optimization. And based on these research findings, our project will focus on improving these limitations. We plan to introduce more models, develop better ensemble strategy, and implement automated model selection process. We hope to improve the accuracy and efficiency of early diagnosis. Now, I will hand it over to Lü Wenjie.
I'm going to talk about the proposed method. Here is the architecture of our proposed method. The first step is using the raw data as our input, and then using the data preprocessing, and then do the feature engineering, feature selection, then use models to implement the data, and next step is about the hyperparameter optimization, and the next one is evaluation metrics, and the last one is final output result. And in this framework, we have do the evaluation studies on two steps. One is the data preprocessing, and another one is hyperparameter optimization. Okay, the first step is about the data preprocessing. We use three different kinds of method to do this preprocessing. The first is handling the missing value. we have two different types of variables in this data set. One is continuous, which we input the median to handling the missing value, and another one is about the category variables. We use the mode to input the missing value, and the second techniques we use is about the scaling and normalizations. We apply the min-max scalar to normalize feature to a range between 0 and 1. And the last one is about the SMOT. We use SMOT to generate some samples for the minority classes to improve the balance. And the next step is about the feature selections. We use two different kinds of method to do this feature selection. The first one is about the RFE-CV. In RFE-CV, we have to choose one base estimator, so we choose the light GBM as our estimator, and using the light GBM to do the RFE-CV with tenfold cross validations to find the best feature selections using F1 score. And what can light GBM do? Light GBM is a gradient boosting framework that can find the feature importance ranking, so we can use these two techniques to do the feature selection. And the next step is about the model implementations. We choose 5 different kinds of basic machine learning model. So here is the 5 models. The first one is random forest and XGBoost and gradient boosting, and the basic model like SVN and logistic regression. And the next one is about the hyperparameter optimization. We use the Aptuna framework to do this parameter optimizations, and the Aptuna give us some objective function to do this parameters tuning. And the last two part is about the evaluation metrics and the final output. We use 3 different kinds of evaluation metrics. The first one is about the accuracy, and another one is F1 score, which can shows the performance on the imbalance data, and last one is ROC AUC. Okay, let's talk about the experiments. The data set is from the CAGO, and it includes some dementia patients' healthy data, and include the imaging biomarkers, clinical parameters, and social demographic informations. Okay, in the data set, we can find there have the significant class imbalance. Just like in the real world, the dementia is more less than the non-dementia. And in these two plots, we can find the age and gender distribution of individuals with or without the dementia diagnosis, and the higher age may be led to the higher diagnosis rate in the dementia. And here is about the smoking habits with individual with dementia or not. And in these two plots, we can find maybe EX smoker can cause diagnosis dementia highly than never smoker. And this is the correlation matrix with the variable in the data set, and it shows the relationship among demographic, clinical, and imaging features. Okay, about the experiments environments, we use our own notebooks to do these experiments. So here is our own notebook. And about the model comparisons, we used 5 different kinds of the baseline model, and we found these 5 models are also the state of the art in this topic or in the CAGO, and we use the 3 evaluation metrics to evaluate our model's performance. Okay, next one is about the ablation studies. We have 4 different scenarios to do this ablation study. The first one is base model without any smooth or obtuna technique to do that. And another one is only use smooth to deal with the imbalanced data. And another one is about the only use the obtuna to tuning the parameters. And the last one is combine the smooth and obtuna together. Okay, and here is the gradient boosting with obtuna for an example. As you can see in the code, we have defined a objective function to make the obtuna find best an estimated link rate, mass step, and subsamples. Okay, here is about the ablation study F1 score comparison. As you can see, in the base models have in 5 different kinds of models shows that didn't have the great performance. And here is about the accuracy. You can see in the only use obtuna and the base models. In these two kind of versions, the accuracy are always high. I think maybe it's a kind of like overfitting or just the model guessing the answer. And here is about the ROC AUC. As you can see, the using smooth or smooth plus obtuna has more good performance on the SVM than others. Okay, here is about the mean performance metrics by the configuration types. As you can see, because the dementia or not is a very imbalanced data, so we choose F1 score as our first tier evaluation metrics to be focused. So in here, you can see the smooth have highly more higher than other. And here is our experiment results. We can find the best model is about gradient boosting with smooth. It has the 0.426 per on F1 score. And on the left hand side, you can see in these models, we do the SHAP. We can find some like age, study, education years as our highly feature importance columns. And the last one is about the conclusion. We propose a method that can reduce handling the leading value and do some feature selection and whole machine learning pipeline to predict the dementia. And in the results, we achieved the we have achieved a higher F1 score in the imbalanced data and get the accurately prediction. The benefits we bring is about the enhanced early diagnosis and for the dementia patients, and provide a scalable, cost-effective solution to diverse healthy care setting, and lays the groundwork of the commercial applications in telemedicine and healthcare analytics. And here is our reference. And about the code part, I'm going to heading over to the Liu Chen.
I will walk you through the code of this project. At the beginning of our code, we imported several relevant packages including our Feynman models, logistic regression, gradient boosting, random forest classifier, XGBoost, and SVM. We also imported other necessary packages for evaluation metrics and such. After that, we create numerous data visualization charts to help us better understand the contents of this dataset. As you can see, each cell outputs different types of visualizations, like data information, and we do some data preprocessing and visualization like a pie chart and bar chart and pair plot and KDE plot, box plot for the data distribution for age, and the other features. And next part, we generate some bar chart for the male and female different target. And next part, we generate the correlation matrix heat map. That offer can help us to better understand the content of this dataset. After analyzing the visualizations, we tried using the RVCV combined with light GBM to identify the most relevant features. Then we experimented with building 5 different models with the evaluate model function, and it will output the F1 score accuracy, ROZ AUC classification report, confusion matrix, and precision recall curve. We choose to use the binary F1 score as our main comparison metric because the dementia dataset is imbalanced. Patients with dementia are the minority, yet they are the key focus of this project. Initially, we built the models using basic default hyperparameters. As you can see the comparison table here, like this cell output, you can see the classification report, confusion matrix, PR curve, and you can see the comparison table here is the base model results. Then we created a version using Smooth, and you can see the same output like last cell. It also output the classification report, confusion matrix, precision recall curve for 5 models. And you also can see the comparison table for this Smooth version. Next, we tried a version optimized with Optuna. And this part is the objective function for 5 models using on the hyperparameter searching. And this part we starting Optuna optimization for all models, and the trails I set the 50. As you can see, is at the other contents of output is the searching history. And you also can see the confusion matrix, classification report, and PR curve for this cell like last cell. And you also can see the comparison table for 5 model at the Optuna version here. Finally, we combine the Smooth and Optuna, and you also can see we set the entrails equals 50, and you can see the output of this cell like last cell is also output the classification report, confusion matrix, and the precision recall curve for 5 models, and also output the comparison table here. And to wrap up, we consolidated all this evaluation experiment result into one table and chart. This is the code, and to recognize which one is the best model and try to use the different explainer to generate the SHAP. As you can see, it's the complete result comparison. It concludes the 5 model on 4 different versions, and totally have 20 models. And this is the chart, and as you can see, gradient boosting with Optuna optimization achieve the best result. We also use this model to create SHAP charts to enhance the interpretability of our project. And this figure concludes the age, study, education years, EF, global, SVD, amended score, PS, smoking, physicus, gender, leg count, features. Let's conclude our group's code demonstration. If you want to run this code, please make sure that code and dataset in the same folder. Thank you for your attention.